In A Thousand Plateaus, Deleuze and Guattari propose a mathematical model of smooth and striated space, which essentially rests on two principal sources: the manifold theory formulated by the German mathematician Bernard Riemann, and an account of Riemannian spaces provided by the French philosopher of mathematics Albert Lautman. One of the key ideas Deleuze draws from Lautman is the absolute heterogeneity, characterizing what Lautman presents as the most general Riemannian spaces. Following some suggestion of Deleuze, many authors have understood such characterization in terms of the distinction between topological, that is non-metric, and geometric metric space. On this interpretation, Riemannian space would be, as Deleuze says, a pure patchwork of heterogeneous elements, the most general form of which would be that of a topological space or topological manifold, in contrast to Euclidean space, typically assumed as a model of homogeneous metric space. This contrast indeed features much of the distinction between smooth and striated space, as well as Deleuze's theory of rhizomatic and arborescent multiplicities. However, while such interpretation is plausibly consistent with Deleuze's reading of Lautman, as we shall see, it has nothing to do with what Lautman had in mind. In other words, what Lautman means by the absolute heterogeneity of the most general Riemannian spaces has no relation to the non-metric metric distinction. Nevertheless, what I would like to show is that it is precisely Lautman's interpretation, rather than the non-metric metric distinction, which may allow us to bring out not only some often overlooked aspects of smooth and striated space, but also what, in my view, is the main philosophical problem Deleuze draws from Lautman. To understand what Lautman means by the absolute heterogeneity of the most general Riemannian spaces, we must discern the problem underlying his account. Lautman's account, as Deleuze and Guattari reported in A Thousand Plateaus, begins as follows, quote, "Riemann spaces are devoid of any kind of homogeneity." Lautman, however, actually writes, quote, "Riemann spaces are on the contrary devoid of any kind of homogeneity." To what does he refer? In other words, contrary to what are Riemannian spaces absolutely heterogeneous? According to Lautman, modern geometry presents two principal conceptions. The first is the one introduced by Riemann in his famous 1854 habilitation lecture on the hypothesis which lay at the foundation of geometry, while the second is that expounded by the German mathematician Felix Klein in his celebrating 1872 so-called Erlangen program. Following his master, the great French mathematician Élie Cartan, Lautman argues that these two conceptions are opposed to each other, and that Riemannian spaces and Riemannian geometry are in contrast to Klein spaces and Klein geometries. To understand Lautman's argument, we therefore need first to briefly recall the Riemannian and Kleinian views, respectively. Riemann's conception rests on two fundamental notions. The first is that of a manifold of arbitrary dimension. A manifold is what we would call a topological space or topological manifold, in which, as Riemann says, one disregards any metric consideration. On such manifolds, Riemann introduces then a metric structure, and more precisely a so-called Riemannian metric. The metric, roughly speaking, is what allows one to determine the infinitesimal distance between points, curves, angles, and so on. A Riemannian space, or Riemannian manifold, is a topological space, and more precisely a continuous and differentiable manifold provided with a Riemannian metric. The second fundamental notion is that of curvature. The curvature, Riemann says, defines the deviation from flatness of a manifold. That is, how a manifold, which may be a curve, a surface, or a space of any dimension, deviates locally, which means in an infinitesimal region, from being Euclidean. Riemann explains that the curvature may be either variable or constant. That is, it can vary, as Lautman states, from point to point, or it can be everywhere uniform. Riemann shows that the spaces of constant positive, zero, or negative curvature form a spectral class. This class corresponds to the spaces of Euclidean and non-Euclidean geometry, that is spherical and hyperbolic geometry. Riemannian geometry is therefore the study of n-dimensional Riemannian spaces which may be either variably or constantly curved. Klein's conception, as expounded in his Erlangen program, instead rests on the idea of applying group theory to geometry through the so-called theory of transformation groups. According to this theory, any geometry and its corresponding space is defined by the invariant properties preserved under the action of a group of transformations or symmetries, which Klein calls the fundamental group. For example, the properties of figures remaining unchanged under the group of isometries or rigid motions, that is, translations, rotations, reflections, define Euclidean geometry and Euclidean space. Klein and others demonstrated that the fundamental group of each geometry forms a subgroup of a larger one associated to another geometry. This allowed a unification and classification of all geometries known at the time: Euclidean, non-Euclidean, affine, projective, including topology, essentially understood in a modern sense of the study of invariance preserved by topological spaces under so-called homomorphisms, that is, continuous transformations. Klein geometry is therefore the study of Klein spaces, which are spaces on which a symmetry group is defined. Now, why for Lautman are Riemannian spaces and Riemannian geometry opposed to Klein spaces and Klein geometries? Lautman's argument is made clear by Cartan. What characterizes Klein's conception, Cartan argues, is that, quote, all Klein spaces are homogeneous in the sense that their properties are invariant under the transformations of the corresponding fundamental group. From this point of view, Cartan explains topological spaces are the most homogeneous, since they can be continuously transformed into each other while remaining topologically equivalent, that is, homomorphic. In general, Klein spaces are homogeneous because they involve transformation that act, as Lautman says, quote, in the same way on all points of space. Mathematically, this means that they possess a so-called transitive group action, according to which, for any 2 points of space, the group transformation takes one point to the other so that all points are equivalent to each other. From a geometrical point of view, this assumption makes Klein spaces homogeneous, that is everywhere the same, and isotropic, that is the same in every direction. Thus, Klein spaces are characterized by absolute homogeneity. However, the only class of spaces satisfying such conditions is that of constant positive zero or negative curvature. And since the curvature of Riemannian spaces, as we have seen, may be variable from point to point, no transitive group action can exist in such spaces because there are no equivalent points. Therefore, except for the trivial case of the identity transformation, Riemannian spaces are generally not invariant under any group of transformations or symmetries. Cartan concludes that Riemannian geometry does not fall within the Erlangen program because a Riemannian space, quote, does not admit in general any kind of homogeneity. In other words, in general, Riemannian spaces are heterogeneous, that is everywhere different, and anisotropic, different in every direction. They are characterized by absolute heterogeneity. Lautman's point is therefore that the absolute heterogeneity of Riemannian spaces is in contrast to the absolute homogeneity of Klein spaces. This contrast is understood from the point of view of the group theoretical approach to geometry introduced by the Erlangen program. On this view, heterogeneity and homogeneity define the degree of symmetry of spaces and geometries. Absolute heterogeneity means non-invariance under any non-trivial symmetry group. Absolute homogeneity means maximal symmetry or invariance, that is, homogeneity and isotropy. This interpretation also explains what Lautman means by the most general Riemannian space. In his account, Lautman argues that an infinitesimal region or neighborhood of a Riemannian space looks like a small bit of Euclidean space. This means that locally, but in general not globally, a Riemannian space can be assimilated to a Euclidean space. However, he points out, quote, "The connection from one neighborhood to the next neighborhood is not defined, so that a most general Riemannian space turns out to be an amorphous collection of juxtaposed pieces that are not attached to each other." Although I cannot provide here a detailed explanation of this passage, we shall see, at least intuitively, the problem it entails. But the point for the moment is that by a most general Riemannian space, Lautman means a space of variable and not of constant curvature. Indeed, as we have seen, all spaces of constant curvature are not only special cases of Riemannian space, but, more importantly, they are all included in Klein geometries. As a result, the most general Riemannian spaces are heterogeneous spaces of variable curvature, while Klein spaces are homogeneous spaces of constant curvature. It is worth noting, however, that Klein and the mathematicians who followed him did not perceive the contrast with Riemann's conception. This is because by presuming a condition of homogeneity in order to apply group theory to geometry, they dismissed a priori Riemann's idea of variably curved manifolds. The contrast instead, as Lautman, again following Cartan, points out, emerged with the advent of Einstein's general theory of relativity. The reason lies in a crucial difference between the special and the general theory. Special relativity rests on a pseudo-Euclidean space of constant curvature, called Minkowski space. The symmetry group of Minkowski space is given by the so-called Lorentz transformations, which are distance-preserving transformations between inertial frames of reference. General relativity, instead, is based on a pseudo-Riemannian space of variable curvature dynamically dependent on the distribution of matter, so that global inertial frames of reference are no longer possible. Thus, while the space-time geometry of special relativity is homogeneous, that of general relativity is heterogeneous. The consequence is that whereas special relativity satisfies the Kleinian conditions of maximal symmetry, general relativity has, in principle, no symmetry at all, and therefore it is not invariant under any non-trivial symmetry group, as the most general Riemannian spaces. With this analysis in hand, we can now turn to Deleuze. As far as the mathematical model of smooth and striated space is concerned, in general outline, Deleuze defines smooth space as a non-metric multiplicity, an amorphous, non-formal, heterogeneous space in continuous variation. Its primary mathematical model, as drawn from Lautman's account, is Riemannian space. By contrast, striated space is a metric multiplicity, a formal, everywhere fixed and homogeneous space. Its primary mathematical model is typically exemplified by Euclidean space. Now, at first sight, Deleuze's definition seems quite problematic. For example, we have seen that Riemannian space is a kind of manifold provided with a metric structure. Thus, in Deleuzean terms, it would be rather a metric multiplicity, and therefore a striated space. However, Deleuze argues that while being different in kind, non-metric and metric multiplicities are necessarily in relation. Moreover, he insists on the possibility and even necessity of the processes of striation and smoothing that convert, assimilate, translate smooth and striated spaces into each other. In fact, Deleuze points out, smooth and striated space exists only in mixture. Therefore, a Riemannian space may be seen as such a mixture composed, as Lautman states, by a collection of local pieces of Euclidean space. This piece-like local construction is of crucial importance for Deleuze. First, Deleuze draws from it the idea of Riemannian space as a pure patchwork of neighboring little pieces. This allows him to relate Riemannian space to smooth space, conceived as an assemblage of heterogeneous pieces or elements linked together locally, step by step, as Deleuze often says, which amounts to a space in continuous variation. Second, Deleuze similarly thinks of a piece-by-piece construction of the plane of consistency or immanence, as opposed to the pre-given structural global whole of the plane of organization or transcendence. Third, a similar constructivism defines the architecture of philosophical concept in what is philosophy. And finally, one of the central ideas of Deleuze's pluralism and empiricism is that of a harlequin world made up as a patchwork of non-totalizable fragments. We shall see the key problem underlying this view. Nevertheless, the main point of Deleuze's reading of Lautman appears to be his claim that a most general Riemannian space can be defined, quote, without any reference to a metric, which is why he takes Riemannian space as a model of smooth space. Now, in my view, Plotninsky has proposed the most convincing interpretation of Deleuze's claim. In his view, Deleuze is thinking of topological spaces rather than Riemannian spaces properly, and ultimately of topology rather than geometry. As a result, Plotninsky has suggested that a most general Riemannian space might be understood as the topological space that, as we have seen, in fact underlies any Riemannian space. This interpretation has the merit to account for Deleuze's reading of Lautman according to the non-metric-metric distinction. The problem is, however, that this interpretation has little, if any, relation to what we have seen to be Lautman's interpretation. For example, Lautman thinks of Riemannian spaces as always provided with a metric. Of course, this does not mean that he disregards topological issues. On the contrary, they are crucial in his more general analysis. But, at least for what we have seen, there is no question of topology in Lautman's account. Moreover, from Lautman's point of view, interpreting the most general Riemannian spaces as topological spaces would be even mistaken. As we have seen, while a most general Riemannian space is heterogeneous in that it is not invariant under any non-trivial symmetry group, a topological space is homogeneous, being invariant under the group of all homomorphisms. Therefore, while it is true that a topological space underlies any Riemannian space, at least for Lautman and Cartan, they are in some sense diametrically opposite spaces. In light of these considerations, I would like to show the relevance of Lautman's interpretation, rather than the non-metric-metric distinction, in order to understand some aspects of smooth and striated space, and finally, the philosophical problem Deleuze draws from Lautman. Throughout Thousand Plateaus, Deleuze and Guattari distinguish heterogeneous, rhizomatic systems and homogeneous, arborescent systems. The distinction, they explain, depends on a double treatment of what they refer to as variables. One that puts them in continuous variation, and another that extracts constant and invariance from the variables. For example, when linguistics studies language by identifying phonological, syntactical, or semantic constants, or by determining, quote, constant relations between variables, now, linguistics reduces the variability and heterogeneity of language to a homogeneous system defined by, quote, structural invariance. However, Deleuze and Guattari emphasize the distinction between heterogeneous and homogeneous systems is not due to the opposition between variables and constants, but on two opposing approaches to the variables, because, quote, the constants are drawn from the variables themselves. In other words, systems are differentiated by applying invariance constraints to a primary non-invariance, so that homogeneous systems are produced by imposing constancy conditions on a primary variability. The same argument holds for smooth and striated space, as well as we have seen, for the main reason opposing Riemann's and Klein's conception according to Lautman. The heterogeneity of smooth space depends on its continuous variation. This, however, should not be understood as a topological continuous transformation, because in that case all smooth spaces would be equivalent. On the contrary, continuous variation expresses a variability which implies non-invariance, so that smooth spaces can be seen as the most general Riemannian spaces as heterogeneous spaces of variable curvature. By contrast, striated space also supposes a continuous variation of the variables, but to which a constant value is assigned. This constancy renders striated spaces homogeneous. Deleuze rightly considers Euclidean space as paradigmatic in that sense. Being everywhere uniform, Euclidean space is the simplest model of maximally symmetric space, as defined, Deleuze says, by Euclid's invariance. That is, as we have seen, the invariance of the isometry group. Therefore, striated spaces can be seen as Klein spaces, as homogeneous spaces of constant curvature. In this sense, also the spaces of classical, non-Euclidean geometry, that is spherical and hyperbolic geometry, should be considered as striated spaces. Furthermore, Deleuze argues that the continuous variation of smooth space also affects its directions and frames of reference. The variability, he writes, the polyvocality of directions is an essential feature of smooth spaces of the rhizome type. Deleuze indeed describes the rhizome as composed by directions in motion. The desert, one of the paradigmatic examples of smooth space, is inhabited by the nomads by adding, quote, desert to desert, step to step, by a series of local operations whose orientation and direction essentially endlessly vary. In other words, smooth space involves ceaseless directional changes, continuous variation in direction. By contrast, striated space is, quote, the limit form of a space striated everywhere and in all directions, where, crucially, they are taken as constant directions. Moreover, Deleuze argues that striated space is defined, quote, by invariance of distance through an interchange of inertial frames of reference. This is an interesting point for at least two reasons. First, because it is an implicit but rigorous reference to the invariance under the Lorentz transformations, which, as we have seen, characterizes Minkowski space of Einstein's special relativity. Second, because it suggests that Deleuze does not include among striated spaces the pseudo-Riemannian space of Einstein's general relativity, which indeed extends to arbitrary non-inertial frames of reference, and therefore is, as we have seen, in principle devoid of any symmetry. As a result, while smooth spaces are, again, as the most general Riemannian spaces, anisotropic, striated spaces are, as Klein spaces, isotropic. But there is a final important aspect. Deleuze refers to Riemann's distinction between multiplicities, or rather manifolds, independent of the situation or position, or instead dependent upon it. From this distinction, Deleuze draws the idea that position-dependent multiplicities are non-metric and intensive, while position-independent multiplicities are metric and extensive. Despite the crucial importance of the intensive-extensive distinction for Deleuze, it is worth noting that Riemann's distinction has a further implication. Riemann remarks that bodies or figures are position-independent only if the curvature is constant, because only in this case they can be moved isometrically. Indeed, if the curvature is variable, the motion of bodies or figures must depend on their position and direction, and consequently, an invariant, rigid body motion cannot exist. Therefore, since the dependence or independence of position implies manifolds of respectively variable or constant curvature, Riemann's distinction involves, once again, the contrast between heterogeneity and homogeneity in Lautman's sense. Now, in my view, this encloses the most important philosophical problem Deleuze draws from Lautman. Since the absolute heterogeneity of the most general Riemannian spaces implies a dependence of position, The problem is then how to compare the local pieces of Riemannian space, Deleuze says, quote, the ones with respect to the others. Incidentally, note that this crucial statement has curiously not been translated in the English edition of A Thousand Plateaus. But anyway, in other words, we have seen that each local neighborhood of Riemannian space reduces to a piece of Euclidean space. The point, however, is that such pieces are, as Lautman says, not attached to each other, because each one is at every point and in all directions absolutely different. What Deleuze draws from Lautman is therefore not much the nonmetric, topological, or metric geometrical nature of Riemannian spaces, but more profoundly that once affirmed that a Riemannian space is a collection of local pieces of space, the problem is how to link them to each other. Evident that this is the central point for Deleuze is found in a passage of his lectures. In explaining the difference between the plane of consistency and the plane of organization, Deleuze argues that the former is constructed by local operations as a Riemannian space. However, the plane of consistency, he emphasizes, would be catastrophic not only if it were to break the plane of organization, but more importantly because of dangers proper to itself, namely, quotes, that all of a system of linkages may not be done, that its local construction may not be prolonged too long. Thus, while the idea of a step-by-step, piece-by-piece construction is essential for smooth spaces, the plane of immanence, philosophical concepts, and in the end for Deleuze's entire philosophy, the problem for Deleuze is that the linkage or connection enabling the construction is never a priori given or granted, as the most general Riemannian spaces reveal. How to link or connect then heterogeneous elements while retaining their heterogeneity? This is the point of Deleuze's reading of Lautman, and in my view, one of the key points of Deleuze's philosophy itself. Thank you.